tell you that we can actually extend this formula to where A and B need not be coprime. You'd say I was mad, surely, wouldn't you? But it can be done. Watch. So let's get straight to the maths here, alright? For those of you joining us, perhaps some of you skipped the history. Well, you shouldn't skip the history. No, of course not. So here's the formula that I showed you at the end of the last lecture. If A and B are coprime integers, and suppose that A is greater than B, then there exists a pair of integers, S and T, such that AS plus BT equals 1. And what if I were to tell you that we can actually extend this formula to where A and B need not be coprime? You'd say I was mad, surely, wouldn't you? But it can be done. Watch. AS plus BT equals the greatest common divisor of A and B. Or in other words, the greatest common factor of A and B. And this one is always true. There always exists a pair of integers. So I would say that really, from this, the main restriction that we put on A and B has been lifted. And we see a broader truth going on here. Oh, and I'd just like to point out, in case it wasn't already obvious, because A and B were coprime in the specialization, so here, in this particular statement, because A and B were coprime, their greatest common factor equaled 1. That's just the definition of being coprime. So that is why in this particular one, this particular formula, the right-hand side of the equation equals 1, because that is the coprime, that is the greatest common factor of A and B. But some natural questions arise from this, as I'm sure you're aware. The first of which is there a sure way, is there a certain way to find values for S and T? Because if not, sure, it's an interesting statement, but, would there be a way that's guaranteed to find these values of S and T and really make this more concrete? And for that matter, is there a definitive way to find the GCD, the actual value of the greatest common divisor of A and B, without simply traversing all the values less than B? And thirdly, how do we know if it works in general? And I hope to answer these questions in today's video, in the next few lessons. Now, what can be helpful, what you'll probably find helpful, is to see examples of this. And when we do that, we'll probably be using a table. Basically, we're going to draw up a table or a list to see the values of certain sequences, which I'll call Q, R, S, and T, which will have deeper meaning later. In fact, I think I'm going to define them very soon. So we have this algorithm, alright, and it's called the extended Euclidean algorithm, that defines sequences of integers. Alright, so let's go through this one by one. R sub I refers to the remainders, which tend towards 0. So the initial values for R sub I is sort of, you could say, our main sequence. It's sort of the most important sequence, arguably. Well, that's not quite true. It's just our main sequence, because it starts, you see, its initial values are A and B. And we know that R is going to be a decreasing sequence of integers that finally attains 0. So it's essentially a non-increasing integer, at least in absolute value, it's non-increasing, at least. And it is a, what's it called? The initial values are A and B, and yeah. So we'll see an example. We'll see an example in a moment of really what I'm talking about, but it's a very important kind of sequence for this algorithm. Now, Q sub I is a sequence of integers which can be used as coefficients in order to calculate S and T. And perhaps predictably in terms of the notation, S sub I and T sub I are sequences that are used to compute the final values of S and T in Bezout's identity. So we have these recurrence relations that define the values in our sequences. And you'll note that Q is defined in a very special way. And generally speaking, Q sub I, essentially, is defined as you can find Q sub I by answering some specific questions. For instance, what is the largest multiple of R sub I that is less than R sub I minus 1? So as you can see, hopefully, yeah, as you can see with my cursor here, this right-hand side of the first equation, the first recurrence relation, is basically R sub I minus 1 minus Q sub I R sub I. So Q sub I is this coefficient. And so another way of viewing it is to ask the question, what is the largest number of geometric squares that fit into a rectangle of side length R minus 1, or R sub I minus 1, excuse me. And the answer to this question, because those two questions are actually identical, as we'll see. It's sort of like considering an arithmetical interpretation versus a geometric interpretation. But they're going to give you the same answer. And that answer will be the value. It'll be stored in Q sub I. And again, we'll see examples of this to clarify. But I'm just giving you some of the theory first. And again, there's this all-important table, or listing, which we'll be able to see. So first, let's just see an example for now. Consider the case where A equals 107 and B equals 37. Now, these are both prime numbers, as is probably obvious. But, you know, what's more important, I suppose, is the implication of that, which is that they are coprime integers, all right? So because they're coprime, we would expect there to be, you know, with this algorithm, which I'm about to show you, we're expecting to get values of S and T such that AS plus BT equals 1. So firstly, we list the first value of R in our sequence. So R sub 0 equals A, which is 107, and then of course R sub 1 equals B, so that's 37. So let's consider these two numbers to begin with, all right? And the question we're asking is, what is the largest multiple of 37 that is less than 107? Well, the answer is actually 74. Because if we add another time, if we add another copy of 37, we would get 111, which is greater than 107. So in order to maximize it, basically we want to choose a coefficient of 2. So Q sub I equals 2. And the reason for that, as you'll see, is the next line. So R sub 2 equals this difference. So what we're doing is we're maximizing. Basically, we have this number here, Q sub I, which is the coefficient. And we want that to be, at least, yeah, we basically want that to be maximized. But the maximum possible that Q sub 1 can be, in order for the next number in the sequence to be positive, is 2. Because, of course, we have 107 minus 74, and that gives us 33. So then we continue this process, and we consider, well, what is the coefficient, what is the largest multiple of 33 less than, or that is less than 37? Well, that's just the multiple 1 times 33. So Q sub 2 equals 1. Then we can write the next formula. So R sub 3, the next one in the sequence, is 4. It's rather drastically lesser than, or drastically less than 33, I would say. And so we continue the process. So now compare 33 and 4. Well, what is the largest multiple of 4 less than 33? And I'm sure all of you have heard of it by now. I've thought of it by now. It is, of course, 32, because 32 is the multiple of 4. So in that case, for that reason, we want q sub 3 to equal 8, because 8 times 4 equals 32. And what is the difference after doing that? Well, after subtracting 8 times 4, we have 33 minus 8 times 4, so following, again, the recurrence relation, we get the result of 1. And from there, it gets much simpler. What is the largest multiple of 1 less than 4? Well, in this particular case, it's pretty simple. Q sub 4 equals 4. And in this case, we get 0 for r sub 5, because, of course, it's 4 minus 4 times 1. So here are some remarks for this. The first one is that really there's no restriction in particular on q sub I being increasing or decreasing. There's q sub I, this column to the right, basically now it's on the right. We don't really know much about these values, other than they're just coefficients, alright? So there's no restriction in particular on q sub I. And that's to contrast it essentially with the sequence r sub I, or basically sequence r. Because for r, we want those values to be decreasing strictly. And the algorithm stops when r equals 0. And that signifies, of course, that the remainder equals 0. The remainder of our calculation. And I'd also like to point out that the greatest common factor of a and b will always be the penultimate value of r sub I. So it is the last non-zero value in the sequence r. So in this case, 1. I just like to make that clear before we move on. And so far, all that we've done is really, it's called the standard Euclidean algorithm, essentially. At least I'm fairly sure it's called that. Because we haven't really extended it. We haven't actually gotten values for s and t yet. But that's what we're about to do, alright? So for our next column, s sub 0 equals 1 by definition. And this is always true, by the way. No matter what a and b are, s sub 0 always equals 1. S sub 1 equals 0. And now for the next computations, what we're doing is we're actually taking s sub I minus 1 and subtracting q sub I times s sub I. That's our computation, I know. So basically 1 minus 2 times 0 is 1. And then we say 0, which is s sub 1 right here, and we're subtracting 1 times 1, because these two are in the same row, so we're subtracting q sub 2 times s sub 2, and our result is negative 1. And then, to calculate the next value of s, or in this case s sub 4, we take s sub 2, so 1 minus q sub 3 times s sub 3. So 1 minus 8 times negative 1, or 1 plus 8, which will be 9. And then we actually get to stop right there, because r sub 5 equals 0. So then for t, we define t sub 0 as 0, t sub 1 as being equal to 1, and then t has a very similar recurrence relation. So basically what we do is we say, what is 0 minus 2 times 1? We get negative 1, or excuse me, negative 2. Then we get 1 minus 1 times negative 2, or in other words, 1 plus 2, well, that's 3. And then for the next value, it's negative 2 minus 8 times 3, or in other words, negative 2 minus 24, so that's negative 26. And that is our final value of t. So as I mentioned before, 1 is last non-zero value in the r column, so we know that 1 is the greatest common factor of a and b, which makes sense, of course, because they're coprime. And we know furthermore that based on these values indeed are the final values of s and t. So 9 times 107 minus 26 times 37 equals 1. And we know that's true now, without doing any further calculations. You can verify that if you want to. I guess, what would that be? 963 minus 962 or something like that? Whatever it would be.